Good evening. Welcome all of you to my this tutorial class. This is my 12 tutorial class. Okay. So in my 1 minute, I am going for previous one. In my previous one, we have discussed about eigenvalue or eigenvector and what is the geometrical interpretation of eigenvalue and eigenvector. Okay. And we gave the definitions and we discuss about uh, what is the eigenspace. Okay, and basically this is our central aim or problem for study the eigenvalue eigenvector. Suppose we have one matrix and we are looking for the small structure of one simpler structure of the matrix such that the all property, okay, main all properties of A is inherent by this small this simpler matrix D. What is what kind of simpler matrix? This is nothing but we are looking for this is on diagonal matrix. A diagonal element will be some maybe zero non-zero number whatever, but rest of the element of diagonal element will be zero. So we are looking forward such we have one matrix A such that is it similar to one diagonal matrix or not. This is was our main aim. Okay, so and this is equivalent to this problem. This is this central problem is to find whether there is a basis vi of v consisting of eigenvectors of a such that a vi equal to lambda I bi. This is our one equivalent condition to a matrix is diagonalizable or not, to find whether there is a eigenbasis or not. Okay, this was our main problem, and we have I I provided one example such that it's may not this is not a diagonalizable matrix. So what we can conclude that every matrix, okay, may or may not be diagonalizable. So we can conclude this by this example we can conclude that every matrix may or may not be diagonalizable, means similar to may or may not be similar to a diagonal matrix. Okay, so what under which conditions a matrix will looks like a diagonal matrix. So this is our aim today. Okay, so I am going for my tutorial class 12. Okay, 1 minute wait. Yeah, so and I will start with example that I in my previous lecture I have also already mentioned that every matrix, okay, every real matrix may or may not have the eigenvalue. Okay, so I will start with one example. Take A equal to 0 minus 1 1 0. What is the eigenvalue of that matrix? Is the eigenvalue of this matrix exist or not? This is my question. Please tell me.
Its eigenvalue exists, but it is in complex numbers. Iota and plus minus iota.
Yes, understood. So, when we are talking about real matrix, we are looking for real eigenvalue. Okay. So here, if we consider if you talk about real eigenvalue or real root of this equations lambda I minus a equal to 0, if we look for real roots of this equation, that time no real root of that this equation exists. Okay, so we can say that no no sir no a does not have any eigenvalue. So In similar way, you can say A does not have any eigenvectors. So here we are not getting, so our central problem was to find eigenbasis of the domain. Okay, so eigenbasis is related to eigenvector. If one matrix does not have any eigenvector, then how will get the eigenbasis? Is it or not? Understood?
Yes, sir.
Risu?
Yes, sir.
Yeah. So these are the some restrictions. Okay. So I am giving to you one necessary condition for existence of eigenbasis. Okay. Suppose you have one matrix. Okay. I am writing the theorem or lemma, whatever you can say. Okay. First, we'll observe few things. Then we'll go for necessary condition of a matrix is similar to diagonal matrix. Okay. Let you have one A. Let A be an real matrix. Okay. N cross N. Okay, this is the notation of n cross n real matrix. Okay, let's take A is an real matrix. Assume that Vi is a, okay, non-zero eigenvector. When we gave our definition of eigenvector, that time we already assumed that non-zero, so we don't have mention again, but I'm writing. Okay, it's mentioned in book, so I'm writing this one. No issue. If you don't want, you can erase it. Okay, because we are eigenvector means you already assume that it's non-zero. Okay, eigenvector of A with eigenvalue lambda. So your Vi is a eigenvector corresponding to eigenvalue lambda. Okay, so take these collections lambda, and also I am assuming another statement, and such that lambda is not equal to lambda j, and also let lambda is not equal to lambda j for all ij. Okay, so we are assuming that Vi is a eigenvector of A with eigenvalue lambda, and also assume that this eigenvalue are distinct. Then what we can say about these collections? One to, yeah, suppose you have n distinct eigenvalue, then we can take collection n, or suppose you have m distinct eigenvalue, then I am taking m, where m is less equal to m. This equals this, the relation is fine or not? Please tell me. Suppose we have one matrix A. Okay, so eigenvalue may be repeated. Suppose you are taking this matrix, take this one, 0 0 1 0. What is the eigenvalue? Eigenvalue is 0 0. Okay, so some repetition may be there, but here I assuming those eigenvector corresponding to distinct eigenvalue. Okay, so this is our collection of eigenvector corresponding to distinct eigenvalue. So suppose one matrix is order n, so at most possible is there is at most n distinct eigenvalue. Okay, is it or not? Is it fine?
Yes, sir. Fine.
Yeah. So what we can say about this collection? What we can say about what we can say about the collection 1 to m? What can it means? I am talking about, is it really independent or dependent? What we can say about these collections in with respect to dependency? Okay, please guess what is your answer. Take two to at least first take two. Yeah, lambda 1 is not equal to lambda 2. Corresponding I am getting v1 and v2. What we can say about really dependency or independency of between these two vectors v1 and v2?
Sir, linearly independent.
Yes. How?
Sir, because is different eigenvalue, we get different eigenvector.
No, what is the reason? Yeah.
Sir, for
Because
different.
another
Please tell. Please tell.
because another other eigenvector cannot be written in other in a combination.
Sorry, I am not able to hear you, Risu. Risu, I am not able to hear you. Something is going wrong. Rajesh, can you try it?
Sir, as eigenvalues are different, so we can get different value for different eigenvector for different eigenvalues.
Yeah, different may be depend na. Suppose you
Well,
have 1 1.
uh,
Take 2 into 1 1. So these two vector are different, but they are dependent. So how we can tell that these two are really independent? This claim is v1 v2 are really independent claim. Okay. So what we have to check? We have to check alpha 1 v1 plus alpha 2 v2 equal to 0. So we have to check that alpha 1 alpha 2 0 or not. Is it or not?
yes, sir.
Okay. If we multiply by a, okay, so acting take this one, this is a 0. When a will act on this one, we will get 0. Okay, alpha 2 v2 equal to 0. Is it fine? A acting on this vector will get again 0 because a is a linear map. Okay, so from here we will get v1 plus alpha 2 a v2 equal to 0. Is it or not?
Yes, sir.
So from here we will get alpha 1 lambda 1 v1 plus alpha plus alpha 2 lambda 2 v2 equal to 0. So we can write it like that: alpha 1 v1 lambda 1 plus alpha 2 v2 lambda 2 equal to 0. Okay,
Yes, sir.
yeah. So if you look that lambda 1 lambda 2 are two real number, two distinct. 1 minute, something is going wrong. Okay. How we can tell? Okay, or suppose we are taking that these two are dependent, then what we'll get? We'll get a v1 equal to alpha a v2. Here we'll get the alpha v2 equal to, yeah, we're done. Okay, yeah. So take this one. Yeah, suppose your v1 and v2 are not nearly independent. Okay, I am assuming this one. Oh, okay. Is it fine or
Yes,
not?
sir.
Yeah, I want to erase this one at first. Please allow me to erase this one. Okay. Yeah. So suppose this is our claim. Okay. Take suppose your v1 v2 are not linearly independent, means independent. So there exists non-zero real number alpha such that v1 can be written as alpha into v2. Okay, v1 will can be written as alpha times v2. Okay, is it fine or not?
Yes, sir. Fine, sir.
Okay, so when a will act on both sides, okay, we will get this one. Okay, so what is this one? This one is your lambda 1 v1, and you'll get lambda 2 v2. Okay,
Yes, sir.
and what is your, take this one, what is your lambda v2? It is v1, is it? Okay, so what we will get? We are getting that lambda 1 minus lambda 2 v1 equal to 0, but our lambda 1 is not equal to lambda 2, so this number can't be 0. So this is forced to you that your vi equal to 0. Okay, is it or not?
Yes, sir.
Yeah, since this is 0 because of as lambda 1 not equal to lambda 2, so we are getting vi equal to 0, but v1 is your eigenvector. This one can't be 0, so this is the contradictions. Okay, so corresponding to distinct eigenvector eigenvector corresponding to distinct eigenvalue we are getting linearly independent. Okay, so what we can say about if you have suppose you have these collections I equal to m is the collection of eigenvectors. Okay, is the collection of eigenvector corresponding to distinct eigenvalue lambda I. Okay, suppose you have total m distinct eigenvalue. Okay, and this is a collection of eigenvector corresponding to those distinct eigenvalue. Then what we can say about these collections? What we can
Sir,
say
this
about
collection will be linearly independent,
yeah,
right?
how we can prove it? Yeah, please tell me someone. So for we have proved it for two two eigenvector corresponding to distinct eigenvalue. This is linearly independent. So here we have total m number of eigenvector corresponding to m distinct eigenvalue. So how we can prove that this is linearly independent?
Sir, same way as previous using principle of mathematical induction.
Yeah, you can use the induction. So for base case we already proved. Okay, so now let us assume that this is true for your k. Okay, let us assume statement is true for m equal to k. Okay, now we have to prove so for when your what will be happen for k plus 1, please try to prove it. So assume this one alpha 1 v1, okay, up to alpha k plus 1 v k plus 1 equal to 0. You have to prove that all coefficients alpha 1 up to alpha k plus 1 is equal to 0. Okay, let's try to prove it. Yeah, try to prove it. So we already know about the up to k
Sir,
plus
as
please tell.
k for k, sir, it is linearly independent. Then, so all of the coefficient for lambda k are zero, necessarily zero.
but
So we will get lambda
but
k plus
no,
1 plus vk
this
plus
is
1
the
equal to
another
0.
one. After adding this one, we are getting 0. So up
Yes,
to
sir.
this one, we don't know. This if this sum is 0, then we can tell that the coefficient of up to k is 0. But we don't know about this sum. We know after adding this extra vector, we are getting 0. Okay, so yeah, your argument will not work. So you try to prove in similar from before cases like that. Okay, so this is your we know up to k is 0. Here your k is less equal to n minus 1, this is less equal to n. Okay, no this noise. Yeah, so when a will act on this equation, what will get, will get again, we will get 0. Okay, so we will get alpha 1 a v1 up to alpha k plus 1 a v k plus 1 equal to 0. So after acting a on this vector, again we are getting 0. Okay, so what is this one? This is one lambda 1 v1, okay, up to alpha k plus 1 lambda k plus 1 vk plus 1 equal to 0. So this is your second equation. So we know up to k is linearly independent, we know, so we have to use that one. Okay, so anyhow we have to remove this term. How we can remove this term from here? Oh my god, it's not working. Oh, something. Okay, yeah, it's fine, thankfully it's working. So we have to remove this term. How we can remove? We have two equations, 1 and 2. How we can remove this term? Please tell. You have two equations.
Sir,
Yeah, please tell.
put the value of lambda k plus 1 into vk plus 1 from equation 1 to equation 2.
Or we can, this is a little bit difficult, not much more, but we can multiply 1 by lambda k plus 1, then we can subtract. Is it or not?
Okay. Yes,
Yeah.
sir.
We can multiply equation 1 by lambda k plus 1, okay, then we can subtract equation 2. Then what we will get? We will get lambda k plus 1 minus lambda 1, okay, alpha 1 v1, okay, plus, okay, this is taken font, plus alpha 2 lambda k plus 1 minus lambda 2 v2, okay, up to alpha k lambda k plus 1 minus lambda k vk equal to 0. Okay, so we know up to this one, up to vk, we know that this is a linearly independent and every term is here is non-zero. Okay, so we can check that full this term. If we collection full this term, we will get, what we will get? Yeah, 1 minute. I did little bit mistake. Okay, because we want that. Okay, no issue. So again, if you can check that, again we will get this is a linearly independent vector. If you want, you can check. So again here we will get that alpha 1 up to alpha k equal to 0. Is it fine? Okay. Okay, so come to your equation 1, then what we will get? Oh my god, it's not working. Come to your equation 1. Okay, so equation 1, what we will get? After putting this value, we will get alpha k plus 1 vk plus 1 equal to 0. Is it or not? Is it fine?
Yes, sir.
Okay, then this is your non-zero vector. Then what will get? This one is 0. So we are getting that alpha 1 up to alpha k plus 1 is 0. So by induction hypothesis we can say that this collection of eigenvector corresponding to your distinct eigenvalue is linearly independent. Okay. Is it fine?
Yes, sir.
So now I am giving to you one necessary conditions for existence of eigenbasis. Okay. Necessary conditions, okay, for existence of eigenbasis, okay, for a matrix A. Okay, so this is your theorem. Okay, let A belongs to your n cross n real number, sorry, n cross n real matrix. Okay, and also if A, so please tell me, this order of A is n, so what is the maximum possible number of eigenvalue of A?
And
N. Okay, so if I assume that if A has n distinct eigenvalue, then what we can say about A? Suppose if A has n distinct eigenvalue, okay, if A has n distinct eigenvalue, then what we can say about A?
sir, A is diagonalizable
How?
because corresponding to distinct eigenvalue, they are distinct eigenvector would
Okay,
form a basis vector for
Rn. Yeah,
yes, sir.
because we are getting, suppose if A has n distinct eigenvalue, then we are corresponding to that distinct eigenvalue, the eigenvector, okay, will form a basis of Rn. Okay, so we are getting, and previously already I have mentioned that A matrix is similar to diagonal matrix, is it equivalent to existence of eigenbasis of for the domain of that transformations. Okay, so this is all, this proof is very simple. You can prove it by on. Okay, so what are the matrix? You can can you could you please tell me, is there any except this one? Okay, there is any necessary conditions for existence of eigenbasis? Do you familiar with any other any other necessary conditions which will give you guarantee about existence of eigenbasis? And do you familiar with any special type of matrix for which every time eigenbasis will be exist? Some special kind of matrix. Could you please tell me about some special matrix for which we'll get every time we'll get the eigenbasis for its domain? Yeah, I asked two questions. One is, could you please give me some necessary conditions for which A is diagonalizable? means we'll get eigenbasis for Rn. Second one, could you please tell me some special type of matrix for which we'll get the eigenbasis for Rn? I have asked two questions. Except these necessary conditions, could you please provide me another necessary conditions, or could you please tell me about some special kind of matrix for which we'll get the eigenbasis of Rn? Are you familiar with those things or not? Please tell me. Rajesh, are you familiar?
Sir.
Robi? No.
Yes, sir.
Are you familiar?
Sir, I'm not getting. मतलब,
So could you please give me some necessary conditions, necessary sufficient condition or necessary conditions for a matrix will be diagonalizable, means similar to a diagonal matrix. Could you please give me some necessary conditions, or could you please tell me some special kind of matrix for which always will get the eigenbasis for the Rn? Understood or not?
yes, sir. Got it.
Are you familiar with those things? Risu? Yeah, please tell Ravi. Please tell, are you familiar or not?
So I don't know about that.
Okay. No, so I have mentioned here, okay, before I need some inner product concept, then I'll go some special kind of matrix, okay. And before that, I have mentioned only one theorem. Please read from book. I will not go for proof, okay. Suppose let A is your n cross n real matrix, okay, and for so are you familiar with algebraic multiplicity and geometric multiplicity of eigenvector? Hmm? Please tell me.
No, sir.
Oh, Risu,
No, sir.
Ravi,
Sir, algebraic matrices of.
algebraic multiplicity. Okay, so I have to mention these things. I'm okay. Suppose take A is your matrix. Okay, so eigenvalue of A may or may not exist. Okay, this already we have seen. Suppose exists. Suppose lambda is an eigenvalue of A. Okay, then this may be unique, or so maybe unique means one, or it might be that lambda two times, it might be repeated or might not be repeated. Okay, for this example we have seen that 0 is the eigenvalue of A, but two times repeated eigenvalue. 0 is a repeated eigenvalue of this A. So your eigenvalue, this lambda, may or may not be repeated. Okay, if is repeated by two times, is algebraic multiplicity is 2. Is repeated by three times, is algebraic multiplicity is 3. Is repeated by four times, algebraic multiplicity is 4. So algebraic multiplicity of an eigenvalue is nothing but a how many times is repeated. Okay, how many times is repeated for a roots of a characteristic polynomial. Okay, fine.
Yes, sir.
Okay, so what is the algebraic multiplicity of an eigenvalue? Please repeat, someone. Yes, please tell what is the algebraic multiplicity of an eigenvalue?
Sir, it is defined as the number of times certain eigenvalue repeated.
Yeah, so you can tell that how many times is repeated, or so suppose lambda is an eigenvalue of characteristic polynomial, then how many is lambda is there in for roots of characteristic polynomial? Okay, this is the algebraic multiplicity of lambda. And what is the geometric multiplicity? What is the geometric multiplicity? In short, it's written as algebraic multiplicity, it is geometric multiplicity. Okay, in short. So what is the geometric multiplicity of lambda? This is related to definitely geometry. Okay, so in my previous lecture we have seen that corresponding this eigenvalue, okay, we defined, or we get that how we can define, we define like that. Okay, so such vector from Rn such that x equal to lambda x. Okay, we defined this one. Okay, so what we can say about this one? I already
Sir, how many times eigenvector repeated?
no, this is already, this is algebraic multiplicity. This is, I define this one set. Is it vector space or not? Please tell me at first. Okay, in my previous lecture I already mentioned those things. I think you forgot about that. Okay, I'm going for in my previous lecture why I have defined, I define, yeah. So this one is v lambda, we define in such way that x belongs to v such that x equal to lambda x is a vector space of v for any lambda, means any eigen corresponding to any eigenvalue. Okay, for a, if lambda is not an eigenvalue, then if you define this set, always will get always will say that this is an eigenvector. Sorry, this is an eigenspace. But here we have to include that zero vector, because everyone are familiar with that is x may or may not be zero. But in vector space we talk about zero. But you can check that zero is also satisfy this equation. So don't have to include, automatically zero will come here. So we can check that this is a vector subspace of Rn. Here I mentioned V, or you can take Rn. So this is nothing but a vector subspace of Rn. Okay, so this is nothing but a, this is a vector subspace of Rn. Okay, is it fine or not?
Yes, sir.
Okay, so this is a vector subspace of Rn, and we call it as eigenspace. Okay, so this is we called as eigenspace. Okay, so this set form a vector subspace of Rn. Okay, this is related to your eigenvalue lambda. So then, since this is a this is a vector space, so it has some basis. So corresponding that we can count what is the dimension of this one. So it has finite dimension, because we're talking about finite dimensional space Rn. So this dimension is less equal to your n. Okay, then what is the dimension of, this is always less equal to your n, and we call it as geometric multiplicity of lambda, geometric multiplicity of lambda. Okay, so dimension of the eigenspace corresponding to lambda or eigenvalue lambda is called a geometric multiplicity of the eigenvalue lambda. Okay, is it fine?
Yes, sir.
Ruby?
Sir, please repeat once more.
Yeah, so you understood the what is the algebraic multiplicity of lambda? Okay.
Yes, sir.
Okay, so geometric multiplicity. Okay, so you have, suppose lambda is an eigenvalue of a matrix A. So consider this set G lambda x, such x from Rn such that x satisfies this by these equations. So you can check it that this is a vector subspace of Rn. You can check it. Okay, very easily you can check it. So only you have to check they take 2x1 arbitrary x1 x2, so you have to check only this one plus alpha 2 x2 belongs to G lambda. Easily we can check it. Okay, so that time we can say that this is a subspace of Rn. Okay, so since this is a vector space, it has some dimension. So because we're talking about finite dimension na, so its dimension, maximum dimension will be n. Okay, and we call this dimension of this space eigenspace, call it a geometric multiplicity of lambda. Is it fine, Rajesh?
Yes, sir. Fine, sir.
Okay, so what is the relation between geometric multiplicity and algebraic multiplicity? Okay, what is the relation between algebraic multiplicity okay, we can write capital noise, algebraic multiplicity and geometric multiplicity. Okay, so at first we will go for one example. Take this one and take another. Okay, so what is the eigenvalue for this one?
Sir, 1 1.
1 1. Okay, and what are the eigenvector corresponding this one, and what is the geometric multiplicity? Please tell me. Please calculate it. What is the eigenvector for this one? Please tell someone. So we have to find this one. Here I am taking 1. Okay, so we can check that this one 1 0. Okay, where A belongs to R, 0 1 B belongs to R. Okay, this at first take this one. Okay, 1 minute. For here, 1 is the eigenvalue. What is the algebraic multiplicity of 1? Please.
2.
2. Okay, fine. Our next aim is find to geometric multiplicity of 1. Okay, so you have to find the eigenvectors. Okay, so what is the eigenvectors for this one? We can check this one and this one are the eigenvectors of R2. Okay, corresponding A, sorry, eigenvectors of A. Okay, these two are eigenvectors of A. So you have to find what is the dimension of this eigenspace. Okay, you can check that lambda 1 will get full R2. You can check it. Okay, because this G1 will be generated by these two vectors. Okay, and these two are linearly independent already, and these two are basis of R2 also. So here we will get G1 equal to full R2. Okay, is it fine or not? Please tell me.
Yes, sir, fine.
Yeah, so what is the geometric multiplicity of 1? Here I am getting also 2. From here we could not we could not get any relation, but here we will get some relations. So what are the eigenvalue of, what is the eigenvalue of B? Please tell me. What are the eigenvalue of B? Base 1. Okay, you can check it. Only eigen, you have only eigenvalue 1 and 1. See, repeated. So what is the you can take 1 and 1. Then what is the algebraic multiplicity of 1? What is the algebraic multiplicity of 1? Please tell me.
So 2.
Yeah. And find the eigenvector. Eigenvector of B. What will get? Please tell me. One can check that we'll get this one. This one. Okay, means we'll get eigenspace of eigenvalue 1, we will get this one. A belongs to R. You can find it. Okay, so this is a subspace of R2. What is the dimension of this one? Hey, what is the dimension of this one? Please tell me.
Two, no, sir.
Oh, what is the basis of this one? Basis of this one is only this one. Otherwise, all other are linearly dependent. Only this one. 1 0 is the basis of this one. So dimension of this is 1. Is it fine or not?
Okay, sir, 1 1. Yes, sir.
Rajesh, are you agree?
Yes, sir.
Rishu?
Yes, sir, agree.
Yeah. So what we are getting from here? Here we can observe. This is your geometric multiplicity. We can observe that geometric multiplicity is always, okay. Here I am getting strictly, okay, but here we got equal. So someone can prove that geometric multiplicity is less equal to your algebraic multiplicity. Okay. Okay.
Yes, sir.
You can prove it. Okay. And if you observe here, when we are taking about n distinct eigenvalue, okay, n distinct eigenvalue. So what is, suppose take lambda 1 is an eigenvalue of a. So what is the geometric multiplicity of lambda 1 for this case?
Sir, 1.
1. And what is the geometric multiplicity of lambda 1?
1. 2.
Yeah, because all eigenvalue are distinct. Okay. Is it or not?
Yes, sir.
All eigenvalue distinct, and you have to satisfy this one, and always you have to remember this is always strictly greater than 0. Is eigenvalue geometric multiplicity has to at least 1. Okay, if eigenvector exists. If no it does not,
Okay.
not exist, then we will not talk about geometric multiplicity and algebraic multiplicity. Okay, so always this has to greater than 0. Okay, you can tell about like the greater equal to 1. Okay. Okay, it's fine. So here we can observe that for this case algebraic multiplicity and geometric multiplicity of eigenvalue are same. Okay, is it okay or not?
Okay, sir.
Okay, so my
Yes, sir.
question
Okay.
is this the exact necessary condition for a matrix, the diagonalizable matrix? For this case we are observed that if we have n distinct eigenvalue, that time algebraic multiplicity and geometric multiplicity both are same, corresponding one eigenvalue of the matrix A. So my question is the enough necessary condition for a matrix is diagonalizable? This is enough. This is not necessary. This is a if and only condition for a matrix is diagonalizable. Okay, suppose you have one matrix n cross n real matrix. Okay, them.
Sir, your voice breaks in between.
Right now it is fine. Hello, it is fine.
Yes, sir.
Okay.
Yes, sir. Fine. At certain time it breaks, sir.
Oh.
Okay, we'll continue.
Okay. So here in this theorem we observe that here your algebraic multiplicity and geometric multiplicity are same for this case when you have n distinct eigenvalue. Okay, you understood why algebraic multiplicity and geometric multiplicity is same? Ravi, could you understand?
Yes, we got it.
Okay, you got it. So my question is this the enough conditions for a matrix is diagonalizable or not? This was my question, and answer is yes. So suppose you have one real matrix. Okay, A is diagonalizable if and only if, okay, algebraic multiplicity and geometric multiplicity of an eigenvalue of A are equal. Okay, this is your if and only if conditions. So I'll not go for proof. Okay, so my time is already over, and so I was talking, this is your if and only if conditions. Okay, understood or not? Please tell me.
Yes, sir.
Okay, so here I am stopping my lecture.